All right, so now we're going back to 6.4, specifically part 2. We have everything we need to be able to look at the Gram-Schmidt process. And so we're going to go through the whole Gram-Schmidt process of changing a basis into an orthogonal basis. So here's the goal of the Gram-Schmidt process. So given a basis, x1 to xp of a subspace, let's call it subspace H. So given just a regular basis of a subspace H, we want to construct an orthogonal basis. No period. Let's go ahead and write it. The orthogonal basis will be V1 to VP of H. So remember, there can be multiple sets that could be bases for a subspace. We have one basis, and it's not orthogonal, and we want to use it to construct an orthogonal basis for that same subspace H. So let's look at a quick example. Maybe not that quick. We are going to let H be a subspace with this basis. One, two, zero. 1, 2, 2. And so let's call this x1 and call this one x2. So we have a subspace H, we have a basis, and what we want to do is find an orthogonal basis. Of H. All right, so before we actually go through this example, let's get a look at the idea of what's happening, and then we'll actually do the work. All right, so here is the idea. We have these two vectors. Call this one x1. Call this one x2. And these two vectors form a basis for H. What we want to do is to transform them into V1 and V2, where V1 and V2 form a basis, but they're orthogonal. So how do we do such a thing? Well, I drew these specifically. X1 and V1 look the same. We're going to keep that. So we are going to take X1 and set it equal to V1. So we're going to start with a focal point, the same first vector. Oh, sorry, you do not see that. Start with X1, set it equal to V1. All right, and then in this previous example here, we have our x2. All right, but we want something orthogonal, V2. How do we do that? Well, how do we always come up with the orthogonal vector? We always use a projection. A projection will help us get there. So what we need to do, we need to project x2 onto x1. Why would we do that? Because when we do project it down, we're going to come up with some vector z, also known as v2, just in a different position, right? And that's how we're going to do it. Okay. All right, so that means that V2, the vector we're looking for, so we're going to set the first ones equal to each other. So to find the second one, we just need to take this and subtract the projection, and that's going to give us our Z, which is our V2. So we're going to take the original X2 and subtract the projection onto X1 of X2. And remember, we're setting X1 equal to V1, so I'm going to put that in there. All right, so how do we do this? Well, let's look at the example we were given. X2 is 1, 2, 2 minus our projection. So we need to do X2 dot V1 over V1 dot V1 times V1. All right, so we got our 1, 2, 2 minus, if we do X2 dot V1, we're going to get 5, which remember, V1 is the same as X1, so we just dot product these two. Then dot product V1 with itself, we also get 5, and then multiply by V1 as well. This gives us 0, 0, 2. And that's our second vector. All right, so what did we do? So we started with a regular basis for our subspace H. We held the first one fixed, and then to get our orthogonal one, we had to subtract a projection. And so our orthogonal one would be the 0, 0, 2. So we would say that the orthogonal basis for H is the set of vectors. First one should be the same, 1, 2, 0. Second one is 0, 0, 2. And you can check to make sure that these are actually orthogonal, right? Dot product, we should get 0. So this one is our V1, this one is our V2. All right, in the next video, we're going to talk about an orthonormal basis. So we're taking it up another notch.